So I'm going to talk about some of the recent results that we have on interconnection tools for fixed time stability, specifically using Lyapunov-based arguments. And those are going to be also focused on singular perturbations and small game theorems. So this is joint work with my student Michael Tang here at UCSD, and also with Miroslav Krstić, who is also a professor here at UCSD. All right. So the motivational problem for us is this setting of feedback optimization. Sort of like a hot topic these days, where you have a physical system, which is the plant. And the idea here is that you don't want to stabilize the plant. You kind of assume that the plant already is stable, but you want to design a controller that steers in real time this plant to an optimal operating point at a steady state. Okay, that's the setting. And the way this works is that we usually assume that this controller operates, or we don't assume, we design the controller to operate in a slower time scale. So this epsilon here is a small gain that is used to slow down these dynamics. And then the typical argument here to prove stability relies on this time scale separation. So that's why tools like singular perturbations are very useful here. So that's the motivation for us. And again, usually there is some cost function that you want to minimize, which depends maybe on both the states, the state of the controller and the state of the plant. But again, this is at a steady state. Okay, so this is not optimal control. We don't want to optimize transient performance. We want to optimize steady state behavior. Okay. So again, as I mentioned, this is traditionally approached using these tools from singular perturbations when you have some slow dynamics and some fast dynamics. After a change of time scale, usually you ended up with a system that has this type of a structure. The slow dynamics now become your controller, and the fast dynamics usually is the plant now. And then again, as epsilon shrinks and as it goes to zero, you ended up with a singularity here. And that's why this is usually called a singularly perturbed problem. So the underlying assumption, the typical underlying assumption here is that for these fast dynamics, you have this quasi-steady state map H that defines the equilibria essentially for the fast dynamics. And of course, it's parameterized by the input to those fast dynamics, which in this case will be the state X. So for every X, you get a quasi-steady state for these fast dynamics. And the way we approach these problems is we introduce this error state, and then what we would like to do is to characterize the behavior of this interconnected system. And to do that, we decompose that system into two simpler systems, the so-called reduced system and the boundary layer system. And in the reduced system, what we do is that we essentially take a look at the slow dynamics and we substitute Z by the quasi-steady state H of X. We ended up with a system that does not depend on Z. And for the boundary layer dynamics, we essentially characterize the behavior of this error state as epsilon shrinks to zero. So we end up also with a system that has this type of structure where X is taken as a fixed frozen thing. All right, so then the key question then is, okay, if I have these simplified systems, this reduced system and the boundary layer system, then we would like to use the information about these easier systems to say something about the stability properties of the original system, the interconnected system. And that's where these tools are very useful. Okay, so there are many ways in which we can study these types of problems. And today I want to focus on one particular technique, which is called the composite Lyapunov method. And it's a very classic old technique. I think maybe one of the first papers that introduced this technique was this paper in TAC in 1984 by Saveri and Khalil. And it's kind of, I don't want to say easy, but the idea is kind of intuitive. Essentially, you assume that your reduced system has a well-defined Lyapunov function. So you have this kind of nice asymptotic decrease for the reduced dynamics. You assume the same for the boundary layer dynamics, that there exists a Lyapunov function that you can use to analyze the fast dynamics. So you also have stability properties for those fast dynamics. And then once you have those two Lyapunov functions, again, one for the slow dynamics and one for the fast dynamics, then you would like to study essentially a convex combination of those two functions and define a new Lyapunov function and use this new Lyapunov function to study the properties of the original system, the interconnected system. And the goal is to find conditions on epsilon, the timescale separation, such that this composite Lyapunov function actually certifies stability properties. Okay? All right. So the approach, of course, it involves computation of standard derivatives. So if we want to check that this composite Lyapunov function indeed gives you the type of asymptotic stability properties that you want, then we compute the derivatives of the Lyapunov function along the trajectories of the system, the original system. And then the terms that we were studying before for the reduced dynamics and for the bundle layer dynamics that show up on the derivative, and we had assumptions on those terms. So we know that they satisfy these negative bounds, which is good. But then the challenge is usually to deal with these interconnection terms. Okay? And those interconnection terms are the ones where we usually have to impose some conditions to be able to achieve some kind of a stability result. And what Khalil and Saveri show in their paper is that if you impose this type of bounds on those two interconnection terms, that's enough to obtain asymptotic stability for the original interconnected system, as long as epsilon is sufficiently small. And there is a particular formula to construct that epsilon. This is epsilon star here. So this is the classic result again for asymptotic stability. And this is used in many applications. It's surprising how popular is this technique for power systems, for biological systems, aerospace, robotics. There are entire survey papers on how to use this technique for some of these applications. And I should emphasize, in many of these cases, we even have Lipschitz dynamics. And when you have Lipschitz dynamics, checking this type of conditions becomes usually quite easy. But the challenge is when you don't have Lipschitz dynamics, usually how to check these types of conditions. All right. So that's the kind of motivation. So again, this is a very popular technique to study stability properties in this type of singularly perturbed systems. And we would like to extend this technique to study other types of stability notions. Okay? So, of course, again, this was developed for asymptotic stability by Saveri and Khalil, also for exponential stability. The Lyapunov function has some nice quadratic or monomial bound here. But we want to check, for example, okay, why do we want to study this property for something like finite time stability, where you have convergence to the point of interest in a finite time, exact convergence. But maybe even in the case where this time where you hit the point of interest does not depend on the initial conditions. And that's what we call fixed time stability. So key distinction between fixed time stability and finite time stability is that in fixed time stability, you can guarantee convergence to the set or point of interest. And that convergence is exact, and it happens before that time. And that upper bound in that time is independent of the initial conditions. So no matter where you start, how far you start, you will hit the set of interest before that fixed time. Okay? So that's the key idea. So just as an illustration, if I plot a system that is exponentially stable in a logarithmic scale, and I plot the distance to 0, then you're going to get a linear trajectory like this one. But if you plot a system that is fixed time stable, then the trajectories usually have this type of structure where they collapse to 0 again before that fixed time. And that fixed time is independent of initial conditions. No matter how far you start, you get this particular type of behavior. Okay, so it's an interesting property, mathematical property for dynamical systems. It certainly seems attractive, at least from this accelerated perspective. And here is one of the first papers that characterized this notion by Andrew, Praglia, and Arstow. All right. So having said that, so we consider then general nonlinear systems. We see that the origin is said to be globally finite and stable if it is globally asymptotically stable. And on top of that, you have this settling time function that guarantees that you hit the point of interest, the origin, and you stay in the origin for all time bigger than that settling time. Again, for finite time stability, this settling time may depend on the initial condition. But if you have the additional property that the settling time is upper bounded by a constant for all initial conditions, then we say that the origin is globally fixed time stable. And there are tail characterizations for this property. There is a nice paper recent nice paper by Professor Polyakov and I think Denis Efimov with weightings here. And they characterize also this property using KL functions. All right. So the classic way to study these systems, well, there are several ways, but one of the ways to study these systems is via Lyapunov tools. This is one of the standard theorems to study stability properties, fixed time stability properties in dynamical systems. So if you want to study fixed time or if you want to certify fixed time stability, then what you have to do is you need to find a readily unbounded Lyapunov function V, such that when you compute the derivative of that function in time, you get this type of decrease. So you get an upper bound that combines these two terms with different powers here. So one power is between 0 and 1, and the other one is bigger than 1 here. And if you have this type of bound, then the settling time can also be upper bounded by a constant that depends on these four numbers. So the gains here in V and the powers also in the Lyapunov function. And again, this was established I think in a classic result by Professor Polyakov. And as I mentioned before, there are a lot of works that have extended these ideas and relaxed these assumptions in many ways. Okay, all right. So having said that, I think you know where this is going. What we would like to do is to be able to extend the composite Lyapunov method for fixed time stability. Okay, not for asymptotic stability, but now for fixed time stability. So the standard way to approach this is to try to mirror what we did for asymptotic stability. Okay, so we're going to have our singularly perturbed system. We're going to use the decomposition into reduced dynamics and bounded layer dynamics. And we're going to impose the assumption that the reduced dynamics, the reduced system, is fixed time stable via Lyapunov function. So there exists the Lyapunov function V, such that I can use that Lyapunov function to certify fixed time stability for my reduced system. And in the same way, we're going to assume that there exists also a Lyapunov function that we can use to certify fixed time stability of the bounded layer system. And this is uniformly in X. So again, we can go ahead and try our Lyapunov function candidate, the composite Lyapunov function, convex combination of these two individual Lyapunov functions. And then the goal is to hopefully be able to find conditions that allows us to prove fixed time stability for the original system. So if we do the computation for the derivative, we're going to have something that is very similar to what we had before. Again, these terms in boxes, they're upper bounded already by our assumptions up there. So the challenge here, again, is to deal with these interconnection terms. And I think what makes this problem challenging is that in this type of systems, usually we don't have Lipschitz conditions, and we cannot have a Lipschitz vector field that is fixed time stable. So that's why it's not so easy to handle these interconnection terms in the context of fixed time stability. And I believe that's really the reason why this problem remain open for some time, because algebraically is kind of complex. All right, so how do we tackle this problem? So what we found is that it is useful to study this type of bounds if we introduce some auxiliary functions. So we introduce these two types of functions. So v tilde x, that is an auxiliary function that we introduce for the reduced system. And it's going to be the summation of the same function, but with different powers, with the power a1 and the power a2. Just to remind you, a1 and a2 come from these two assumptions here. So a1 and a2. And we also introduce this auxiliary function w tilde for the fast dynamics, the bundle layer dynamics, which again is a summation of the same function with different powers, b1, b2, which come also from this assumption on the fast dynamics here. Okay? So that allows us to define v tilde and w tilde. And we also define the smallest gain k that shows up in the decrease here in the reduced dynamics. So between k1 and k2, we want to find the smallest k here. And we found that under the previous assumption, so under the assumption that we have this fixed time Lyapunov function for the reduced system and a fixed time Lyapunov function for the bundle layer system, then if you satisfy this type of interconnection conditions, and you can guarantee that either this constant v1 is much smaller than 1/2 of this smallest gain, or that v2 is negative, then that's enough to certify that the origin of the interconnected system is fixed and stable again for some epsilon between 0 and epsilon star. So in other words, you are able to extend the composite Lyapunov method from asymptotic stability to fixed time stability by characterizing some interconnection conditions that allows us to get the behavior, again, provided the reduced dynamics are fixed time stable and the bundle layer dynamics are also fixed time stable. Okay? So to compare these conditions where we had before, so this is a useful table. So for asymptotic stability, again, the key assumptions is that the reduced system, again, satisfies this type of quadratic type bound. Same for the bundle layer system. For fixed time stability, we're asking that the reduced system satisfies this type of fixed time decrease and a similar bound for the bundle layer system. And we have some interconnection conditions that are linear in psi1 and psi2 for the first one. And the second also incorporate a quadratic upper bound on I2, the second interconnection condition. But for fixed time stability, we have something that is quite similar if we work with these functions b tilde and w tilde, with a distinction given by these red quantities. So these red quantities essentially characterize the extra conditions that we are imposing on these interconnection terms. So that's the key distinction here. So it is natural to ask how challenging is this, or if it is just a trivial extension of asymptotic stability. And indeed, with these constructions of b tilde and w tilde, one can prove that the composite Lyapunov function has the type of decrease that we want, characterized with a suitable matrix here in the middle, which is kind of what we had for asymptotic stability. There is, however, some gap between showing that this property holds and establishing the fixed time stability property for the system. And that's where these algebraic manipulations come into play. So once you have this type of quadratic decrease for your function in terms of b tilde and w tilde, there are some algebraic manipulations, which are a few pages of manipulations, to go from this type of inequality to this one down here, which is the one that allows us to prove the main result by using the Lyapunov-based characterization by Professor Paul Jacob, for example. So here, gamma 1 will be between 0 and 1, and gamma 2 will be bigger than 1. All right, so going back to the motivational problem, which was on feedback optimization, let's see how would that apply. So again, the goal here was to be able to design a controller that is able to stabilize to steer the physical system to an optimal operating point in fixed time, hopefully with a sufficiently small epsilon as a gain. So we consider plans that have this type of structure, or plans that at least there exists a feedback law, a static feedback law, such that you can put the plan into this form. That's, I guess, the key assumption. There's a typo here, there should be psi1. And to control these plans, we use what we call a fixed time gradient flow. So in standard feedback optimization, the controller is typically some type of gradient flow or Newton gradient flow. So in this case, we're using what we call a fixed time gradient flow, which is very similar to a standard asymptotically stable flow or a Newton flow, but is normalized by these two quantities, where again, psi1 is between 0 and 1, and psi2 is bigger than 1. So then this is the interconnection that is proposed, and here is the epsilon gain that we're going to use to slow down a little bit the controller. So using the classic change of variable for time scaling, then we can put this system into a standard form of singular perturbations. So now we have, again, the fast dynamics up here characterizing the plant, and slow dynamics down here characterizing the controller. And then we can start to use the techniques that we developed. So here the quasi-steady state for the plant is just z equal x, so nothing surprising. The reduced system is obtained by substituting z by the quasi-steady state of the plant, and that will give you a classic fixed time gradient flow. This has been studied in the literature. And then we can also characterize the bundle layer dynamics for the system associated with the plant dynamics in this case. So for feedback optimization, the kind of cost function that you use could be quadratic, or it could also be just strongly convex with a glory Lipschitz gradient, which is usually the assumption. We consider for simplicity quadratic cost functions, which are typical in this case with a positive definite matrix Q. And then we found that indeed you can tackle this problem provided some conditions are satisfied in the controller. So for example, we want the gain here V on the static feedback load acting on the plant to be sufficiently higher than the smallest eigenvalue of the matrix Q that is dividing the largest singular value of the matrix Q multiplied by the matrix A of the plant. And again, as long as you use powers psi 1 and psi 2 between 0 and 1, and the other one should be negative in this case. Again, if under those two conditions, there exists an epsilon star such that the interconnection will be fixed time stable, as long as, again, this epsilon up here is bounded by that epsilon star. So if we simulate this type of systems, again, in the context of feedback optimization, this is the type of behavior that we observed. I'm showing here the distance of both states, x and z, to the point of interest. That's what we were trying to achieve. And I should say that in the past, a few years ago, we studied this problem using only a fixed time controller, but with a plan that was only exponentially stable. And of course, in that case, it was impossible to try to achieve fixed time stability without additional assumptions. So in that case, we were only usually plotting the trajectories of the control law. But here, we want to achieve fixed time stability of the closed loop system. So we want both the states, x and z, to go to the point of interest in fixed time. So that's why we plot here both the states. And I think that's actually the challenging part in this problem. All right, so these results can be extended to systems with inputs, naturally. So in this case, you would like to establish fixed time ISS bounds that have this type of a structure. This function beta is what is called usually a generalized KL bound or a KL fixed time bound, and some class K function V that quantifies the effect of the input, the size of the input on the residual set where you converge. And same ideas can be used in this case. So what we do is that we decompose our system again into reduced dynamics and bundle layer dynamics. We assume that you have a fixed time ISS Lyapunov function for the reduced system and a fixed time ISS Lyapunov function for the fast system. And then there are some interconnection conditions that need to be satisfied now that also incorporate now the input. And as long as you have those interconnection conditions, then we can show that the composite Lyapunov function will satisfy the required bound to establish fixed time ISS again, provided epsilon is sufficiently small. And there is a constructive way to find this epsilon, at least the upper bound, the epsilon that gives you this type of bound. And I should also say that epsilon that we usually find is extremely conservative. So I'm sure there are more efficient ways to find that optimal timescale separation. This method usually gives extremely conservative bounds for epsilon, but at least it gives you the existence of those bounds to start working with something. So this is a result that appeared on a recent paper on TAC. Again, Michael was the leader on this with Miroslav. And this was generalized to input to state stability in this type of singularly perturbed systems. Again, using this idea of composite Lyapunov function. That was the main motivation here. All right. So another application of interest is when we have, for example, systems that have heterogeneous exponents here. So in many cases, it might be, I don't want to say easy, but it's more tractable to study these problems when they have the same exponents in this type of fractional powers. But we wanted to say the case when we have different exponents here. So this is an example where we have that case. So we have different type of exponents in these dynamics. This is the classic notation for that operation that is the absolute value multiplied by the sign of the function to some power. The reduced system will give you something like this. And we find again the bundle layer system will also give you something that has this type of a structure. We can also verify that the interconnection conditions are satisfied. And once we have that verification, then we can establish fixed time ISS for the system. Again, and I want to emphasize these verification conditions involve the functions v tilde and w tilde. Not the original v's and w, but v tilde and w tilde. That's probably the important observation. Another application shows up in the context of tracking in feedback optimization. This is similar to what we had before, where we have a plant and a controller, and the idea of the controller is to steer the plant to an optimal operating point. But here, the cost function you want to optimize is time variant. And it's time variant because it depends on a parameter, beta, and that parameter is governed by some dynamics, some exosystem. And the idea then here is to quantify how far you're going to be from that trajectory. And we use ISS to quantify that type of behavior. So for example, here the plan will be given by a nonlinear system. We typically assume again that this is fixed time stabilizable in some sense. We use a fixed time gradient flow as a controller. And this gradient flow depends on the state of the plant. I want to emphasize that too. And then to study the system, we just work with the tracking error coordinates. And in those coordinates, then the variation of the cost function with respect to the parameter beta, that's the exogenous input that acts on the plant. So this is the U that essentially acts on the system. And taking these two signals as the input, then we can quantify fixed time ISS for this system. And you can see here, as data dot goes to 0, which means as this pi of data goes to 0, then again, the input goes to 0, and then we recover fixed time stability. But of course, when data dot is high, when you have a high variation on time variation on this parameter, then this input here is large, and this input is also large. And in that case, the best we can do is to obtain fixed time ISS. So we get this type of behavior for different values of here of epsilon sub 0, parameterizing how fast data dot is changing. Okay. All right. So that's an extension of the so-called composite Lyapunov method, again, from asymptotic stability and exponential stability to fixed time stability by working with fixed time Lyapunov functions for the bundle layer system and the reduced system, and identify the key conditions on the interconnection terms. And I think that's really the main contribution of that work, which we think is going to be useful for controller design. But once you do that, the next question is if time-scale separation is really necessary for this type of problem. And we know from our past work on asymptotic stabilization in the context of feedback optimization that sometimes it is possible to relax this time-scale separation when you have some type of dissipativity, or maybe you have some type of a small gain conditions that allow you to certify stability of this interconnection. Okay? Now the question is, can we follow that approach too in the context of fixed time stability? So can we take epsilon equal to 1 and try to find conditions so that we will have a fixed time stable interconnection by finding some kind of a small gain condition? So that was an open question, and there are not many small gain theorems in the literature. So we wanted to focus on that problem now. And in the context of asymptotic stabilization, there are many tools based on the small gain theorem. And we wanted to focus specifically on those that are Lyapunov-based here. So this is inspired by the work of Professor Champing-Jean, where essentially you assume that you have Lyapunov functions for the subsystems, individual subsystems. And in this case, as long as some conditions are satisfied by those Lyapunov functions, then you can certify that the interconnection will be asymptotically stable or ISS, as long as some small condition is satisfied. So this will be the classic small gain theorem for asymptotic or input to state stability in nonlinear systems. And the question is, can we find something like this, something very similar to this type of result for fixed time stability? Okay, so that was the next challenge then. Can we generalize this idea of a nonlinear small gain theorem for interconnected fixed time ISS systems? So to answer that problem, which ended up being a bit challenging, we introduced a new type of function. So given a class k-infinite function, if there exists some integer n and some constants, positive constants, ci and pi, such that the function alpha can be written as this polynomial, then we say that alpha is of class k-infinite p. Okay, so we introduce a new family of functions. Again, the class of functions that are k-infinite and also have this type of structure. Now, if the function belongs to this family, if n is equal to 2, so you have two terms in the summation, pi is p1 is between 0 and 1, and p2 is bigger than 1, then we say that that function alpha is of class k-infinite fixed time. And if alpha is class k-infinite, and the inverse of alpha is class k-infinite p, then we say that alpha belongs to class k-infinite minus p. Okay, so we're introducing again two types of functions, those that are of class k-infinite p, and those that are of class k-infinite minus p. And there are some useful facts of working with these functions. The first one is that if alpha is of class k-infinite minus p, then the inverse of alpha is of class k-infinite p. And this is kind of useful because if you have this type of inequality involving two Lyapunov functions, and alpha here is again of class k-infinite minus p, then you have this equivalence between these two inequalities. And it's also useful to know that if alpha 1, for example, here belongs to class k-infinite p, and alpha 2 belongs to class k-infinite minus p, then you also have this type of equivalence between these two inequalities, which are going to be, again, useful because this is usually what you want for a small gain condition. So we found that these families of functions were useful to study this problem. All right. So based on that, what are the key assumptions here? So key assumptions is, as before, we assume that we have some smooth functions or C1 functions, the Lyapunov function for each subsystem. So they should be upper and lower bounded by class k-infinite functions. That's not surprising. And we're going to assume that we have these two functions, psi and gamma I, that are class k-infinite. And we're going to have also this function psi I that is class k-infinite fixed time, such that as long as vi is bigger than the maximum between gamma I evaluated at vj is the other Lyapunov function for the other system, and psi I evaluated at the input, as long as this implies that the derivative of the Lyapunov function satisfies your fixed time decrease, then the assumption is satisfied. Okay, so this is our essentially an extension of what we had for asymptotic stability here. I guess this type of condition. This is for asymptotic stability. So what we're doing is extending that to fixed time stability, that assumption for fixed time stability. All right, so we assume that for each of the subsystems of the interconnection, and we only have two subsystems. And then we have what we call a small gain theorem, or I guess a Lyapunov-based small gain theorem for fixed time ISS, which essentially goes like this. Suppose that these conditions hold. So you have a Lyapunov function for the subsystems, and those Lyapunov functions satisfy this type of fixed time decrease. Okay? Then if there exists this function gamma I hat that is either class k-infinite p or class k-infinite minus p, and as long as you can use those functions to upper bound this function gamma I that shows up here in your second assumption, then the interconnection will be fixed and stable if this small gain condition holds. So as long as the composition of those functions gamma 1 hat and gamma 2 hat is less than the argument, essentially, of the composition. So that's the condition to verify here. And that's what we call the Lyapunov-based small gain theorem for fixed time ISS. So there are some important considerations here, mostly technical. So the proof follows similar ideas as those works by Jean-Ping Chen. There were some works on finite time stability, but it wasn't trivial to extend this from finite time to fixed time for several reasons that are mentioned in the paper. One of the reasons is that if these functions, gamma 1 hat and gamma 2 hat, these ones that you use to verify the theorem, if they belong both to this class of functions, class kp infinite, and there is one function of this containing terms with different powers, then this small gain condition will never be satisfied. So that was a challenge. And that's the reason why we allow this function gamma hat to be either class k infinite p or class k infinite minus p. And allowing that is really what gives us the flexibility to study problems of interest. Okay, so it is actually possible to find examples, and multiple examples actually, where you can find these type of functions that belong to the union of these two sets. Okay? And I should emphasize there is a related result presented recently in a paper by Professor Polyakov, Efimov, and Zimenko, on small game theorems, also for fixed time ISS, where I believe there are some additional extra assumptions on that work. So we're still working on characterizing what are the key distinctions between those two approaches. Our approach was mostly extending what was done for finite time stability in the work by Professor Champing-Chen. Okay, so here's one example. So dynamical system with two states, x and y. Here I have the actual definition of this bracket function. Again, it's the sine function multiplied by the absolute value to some power. And here p, q are positive numbers, r is also a positive number here. The Lyapunov function for one of the subsystems, the x subsystem, is just x squared. If I compute the Lie derivative, I will get this type of decrease. And then I can manipulate this expression to show that as long as x is bigger than this quantity, v dot satisfies the type of fixed time decrease that we're looking for here. So then I can use this as my function gamma 1 in the conditions that I mentioned in the previous slide. Now, for the second subsystem, y dot here, I have a Lyapunov function. I can also compute the Lie derivative from the Lyapunov function and find some conditions under which, again, provided that is satisfied, I have the desired fixed time decrease on w dot. And then I can call this, again, gamma 2. And from here, I can also find the inverse of gamma 2. So now that we have our key assumptions, then we can characterize the small game condition. And we find that as long as these three conditions are satisfied, the first one involves parameters, and the second one involves conditions on the growth of these two functions, f and g, in the example. Then we have that this particular condition will be satisfied for us with the particular gamma 2 defined here and the gamma 1 defined up there. And that in turn implies the small game condition being satisfied with a particular selection of gamma 1 hat and gamma 2. All right. And that, again, implies fixed time stability based on the theorem that I presented before. All right, so now going back to this motivational example, so can we actually, again, use this small game theorem to study the problem of fixed time feedback optimization? So we're going back here. This is the plant of interest. I'm changing notation. Again, this is the plant. Our key assumption is that there exists a matrix P such that essentially the quasi-steady state of this is linear on U. And moreover, that we have some time of, again, fixed time stabilization property for this plant. That's an underlying key assumption. And under that assumption, we consider, again, the fixed time gradient flow that we had before. But here, there is no epsilon. So there is no time scale separation on this controller. And I'm still optimizing a quadratic cost function here. So what you see here is sort of like the gradient of that quadratic cost function. Here's the quadratic cost function. And then we can find now conditions on the elements of this interconnection that preserve the fixed time stability property. And those elements really involve this Lipschitz constant, or I guess this is not the Lipschitz, this constant here that emerges in this inequality for the plant, the largest singular value of the matrix P that shows up in your quasi-steady state mapping, and the largest and smallest eigenvalues of the matrices Q1 and Q2 that emerge in your cost function. So as long as this product is less than 1, that implies that the small gain condition will be satisfied. And then we have fixed time stability here. Okay. So again, plotting this type of trajectories, this is the type of behavior that we observe. And here we use this plant in closed form with a feedback law, static feedback law that puts the plant in this fixed time stabilizable form. All right, so far I have discussed this idea of fixed time stability for continuous time dynamical systems. And I mentioned that what we did is that we extended the composite Lyapunov method developed by Saveri and Khalil to study fixed time stability. And now we developed this small game theorem, originally studied the Lyapunov-based approach, at least by Champing-Chen and coworkers. And we extended that to fixed time stability. So now we would like to be able to extend this type of techniques to hybrid systems. So hybrid systems combine continuous time dynamics and discrete time dynamics. And they're usually characterized by this type of hybrid inclusion. So sometimes it is useful to have a set value continuous time system, so you have a differential inclusion here. And also a set value discrete time system, which is usually a difference inclusion. And that's useful because in many cases, hybrid systems have timers and logic states states like those, and usually those are characterized by set value rules, not just by single value rules. It is also useful because sometimes your vector field might be discontinuous. And in that case, we study regularizations of those vector fields, usually the Krasovsky regularization. So you ended up with a differential inclusion. Okay? So typical examples of hybrid systems include switched systems, impulsive systems, reset control, event trigger control, and so on. And in this description that I'm presenting here, we divide the state space into sets, C and D. It's not really a partition, they could overlap. But the set C describes all the points in the space where the system can evolve according to the differential inclusion. And the set D describes all the set of points where the system can jump according to this difference inclusion. So we call that the flow set, and this one the jump set, and we call this one the flow map. And this is the jump map, and here's a typical trajectory, I guess, of a hybrid system that starts, I guess, from this red point, flows, it gets to a point where it can jump, and then jumps, and then again flows until it hits the boundary of C, and then it stops. And I should emphasize that in hybrid systems, you can have a situation where the solutions, they stop if they essentially leave the set C or the set D. Okay, so having completeness of solutions is not trivial in hybrid system. That's usually something else that you have to prove, or you have to design your system to have that property. So because we have this combination of flows and jumps, solutions of hybrid systems usually are parameterized by two different parameters, one for continuous time t and one for discrete time j. T grows continuously during flows, and j increases by 1 during jumps. And because of that, those solutions are usually expressed in what we call hybrid time domains. So if I want to plot a solution of a hybrid system, I will have the continuous time component, the discrete time component, and then the solutions are these hybrid arcs that we see up here. And this is useful for things like sequential compactness later and robustness. Okay, so there is a framework based on the book by Goels and Felici and Thiel on hybrid systems. All right, so having said that, we study stability properties for sets, so closed sets. So a closed set for the hybrid system is said to be uniformly globally stable if every maximal solution satisfies this step of bound with a class K function here. It is globally fixed time attractive if there exists what we call a hybrid settling time function T that is uniformly bounded, and each maximal solution satisfies that it flows and evolves actually for a period of time that is larger than T. And moreover, you hit the set of interest and you remain there for all times after that particular hybrid settling time T. And it is uniformly globally fixed time stable if it combines these two properties. Okay, so having said that, we can study hybrid systems also using Lyapunov functions. Sometimes we work with non-smooth Lyapunov functions. In this case, we're going to assume that they are actually smooth. They are at least differentiable. We introduce two quantities. We introduce this quantity UC and UD. And UC is going to quantify the worst case increase along flows of that function. Usually this is really a decrease, but I guess it's the slowest decrease. And then this worst case increase is characterizing also the slowest, I guess, decrease of the Lyapunov function during jumps. Okay? And if these are single value elements, if we have a differential equation here and a difference equation here, then this is the classic linear derivative that we had before, and the right-hand side will be just the standard inner product between the vector field and the gradient of the Lyapunov function. Okay, so our goal is to be able to establish Lyapunov conditions to certify fixed time stability properties in hybrid systems. That's the main goal here. So we have the first theorem that says the following. Given a closed set A and given a Lyapunov function B, if your Lyapunov function satisfies the standard plus K infinite bounds, and you have fixed time decrease during flows, characterized again by the typical assumptions on P1 and P2, one is bigger than 1, and the other one is between 0 and 1. You don't have increase during jumps, and as long as every maximal solution flows for sufficient long periods of time, and this doesn't have to be continually, it means for the whole trajectory, you should have enough flows, then you will get the fixed time stability property. There is one additional condition here is that we need to guarantee that we don't have something like Zeno behavior, for example, before you have flow for the necessary amount of time. So there are some conditions here on the nature of the hybrid arcs of the system, but if you satisfy these conditions, then these two Lyapunov-based assumptions are enough to certify uniform global fixed time stability in these types of hybrid dynamics. So some applications, for example, switching systems. So switching system is a particular type of hybrid system. Here, the switching signal sigma is usually more or less a logical state. But we make this assumption that we're going to have what we call a common Lyapunov function, a common fixed time Lyapunov function in this case. And we have a finite number of modes, so we can take the maximum or the minimum, I guess, of these two constants. And then in this case, we study the system as a differential inclusion. Our assumptions can be checked to be verified. And then we can prove that, again, under arbitrary switching, we got fixed time stability, again, because we have a common fixed time Lyapunov function for the system. Another example in the context of impulsive systems. So here I have a differential equation, and I have that every 30 seconds, the state Z suffers this type of jump. So this is a matrix that multiplies Z. So we make the assumption, again, that we have fixed time decrease during flows, and that during jumps, at least I don't have an increase of my Lyapunov function. So I have some conditions on this matrix, lambda I. We can study this system again using the framework that we had before. We introduce an state tau for the timer that evolved between 0 and tau d. We want to study stability of 0 for the state Z. So we can put this system into a hybrid format with flows, jumps, flow set and a jump set. And then we can find, again, a condition here that says that in this case, for any tau d positive, the set of interest will be globally fixed time stable. And we also have a characterization of the fixed time settling time here. So here we don't have conditions on how small tau d can be. It can actually be any positive number just because of the type of assumptions that we have on the system. Now, in many hybrid systems, your Lyapunov function can actually increase during jumps. Okay? And that's okay as long as that is compensated by the decrease during flows. So we wanted to study that case, especially because having fixed time decrease during flows is a very aggressive assumption. So that should allow us to handle some increase during jumps. That was the assumption. And we found that that is indeed possible. So even if you have this type of increase during jumps, you will have fixed time stability under a particular dwell time condition on the jumps. So as long as your jumps are lower bounded by this particular quantity, which depends on the constants of your system, then it will be okay. You'll be able to get a fixed time stability result. And I should emphasize that this lower bound between the jump times is much smaller than the trivial, I will say, dwell time that gives you fixed time stability during flows. Okay? So it's not like you're converting during flows in fixed time to a point, and then you can jump. You can actually have jumps much before that, much sooner than that, and you still be able to get the fixed time stability property here. Right. So some related works on this, of course, a lot of papers by Professor Polyakov and Professor Lyapunov, also from Professor Moreno, Jaime Moreno. And these works will be presented at CBC. The hybrid part will be at CBC this year. And the small beam theorem is under review, but we should put it on archive soon. And I would like to thank NSF and Air Force for the support. And if you have any questions, I'll be happy to answer any questions you may have. Thank you.